Hello student, today also we will continue with the Galois field mathematics. In the last module we have learned algebraic structure for a group, and we have seen also the several properties of a group. We have learned how to test an abelian group. We have also at last we have seen how to see the cyclic property of the group. And we have also seen that a group we form the group with respect to basically two operators. One is the multiplicative operator, another is the additive operator. And in the last part we have taken good example also to check the cyclic group. Some portions I left for your calculations and your checking the cyclic groups. And the example we have also taken, and to check that to test how ZP star with respect to the prime numbers and with respect to the binary operator, multiplication binary operator and identity element 1, how we can check and where we can prove that it is a group. We have also checked that with respect to the number Zn, which is a set of the normal numbers, natural numbers and natural integers, with respect to the additive operator and with respect to the binary, with respect to the identity element 0, how that can form a group. In this class we will proceed from the group and we will enter into ring. So, ring, before entering into ring, let us revisit the conventional algebraic elementary arithmetic, where we are really very familiar about the two operation. One is the addition operation and as well as is the multiplication operation. These two properties of this elementary arithmetic you will find that that is having the maximum closeness or maximum resemblance in an algebraic structure in the Galois field, where actually which is called a ring. This basic property of all the elementary arithmetic you will be able to see that we are recalling all those properties in the construction of a ring. So, ring we will write ring as G. So, usually in this whole lecture, if I write G, please remember that this is the symbol of a group. If I write R, so please remember that it is a symbol of a ring. If I write capital F, then it is a symbol of a field. So, group, ring and field. So, ring is defined like this: a ring R with an operator. Here we have taken both the operators plus as well as the dot. It is a multiplicative operator and the additive operator. So, a ring with respect to this both the operators together, which are operated on this set R, is said to be ring if and only if R is an abelian group. Please remember what was the condition of declaring a group to be abelian group. We saw that if we have the elements say A and B, which are belonging to a set say S, and then if we see that the operator that is operating on that set S, for that operator this relation is true, where A star B is equal to B star A, we declared that the group is equal to an abelian group. So, ring is consisting of a set. This set should be an abelian group with respect to the operation addition operation. So, with respect to additive operator, the group needs to be proved to be an abelian group. I should say that set needs to be proven as a group, and definitely that group needs to be proven as a abelian group with respect to the additive operator. The set R should be proven associative with respect to the multiplicative operator, such that I have taken 3 units or 3 elements from my set R. So, A, B, C are the elements that belong to R, such a way that A star B is equal A star B dot C will be A dot B star C. if it holds good. So, see, the abelian group proof is coming with respect to the additive operator. The associativeness needs to be proved with respect to the multiplicative operator. So, if it is holding good, then also another law is applicable to declare some set as a ring, which is a distributive law. The distributive law says that for all these three elements A, B, C who are belonging to R, with respect to both the operators plus and dot, this should be true. A dot B plus C should be equal to A dot B plus A dot C, and opposite thing, if B plus C dot A is taken, then B dot A plus C dot A should be equal. So, two operators with respect to these two operators, and if all these three are proven to be true, we can declare that this set is definitely a group and also a ring. So, this set is declared to be a ring. It is not only a group, it is also an abelian group and also it is a ring. So, if I tell that there exists a ring, and in the background of your mind you should be able to connect that this is also an abelian group, and definitely it has two operators associated with it, and there exists the associative law, distributive law inside. So, some example now once again. So, the set of real numbers, set of the integers, set of the real numbers, set of the complex numbers, rational numbers with respect to both the addition as well as the multiplication operator, they are all the rings. So, we are well known about the set. If I take the set of all the complex numbers, the rational numbers, the real numbers and the normals, the integers, we will say they are forming a ring with respect to these two operators, and we widely use actually these sets in our day to day life and then any other application of the mathematics, elementary arithmetics. Z4, which is what? This is the set of the natural numbers after modulo n or modulo 4 operation. That set with respect to your additive operation as well as your multiplicative operation, it forms another ring, and definitely how many elements will it have? It will have the 4 elements only. If we come down, we proceed from Z4 to Zn, which is basically after modulo n operation the set of the natural numbers, and that with respect to your additive as well as the multiplicative operator will also form a ring. Now, let there is f plus dot, it is a ring associated, it will be called a ring, it is a ring basically, and let f star, which is also where the element of all the field is actually all the set, the elements of all the set of this f which are A, they belong to this ring R, given that A is not equal to 0, and the set of the non-zero elements of A. So, let f be a ring, then f star which is formed from f, and taking all the where all the elements of belonging to R and A is not equal to 0. It is also a set of the non-zero elements of all the f. So, if I start with a ring and I can form actually f star by taking all the non-zero elements of this f. So, next definition, the field is a ring such that a field can be a ring also such that the f star together with this multiplication is a commutative group. So, to be a commutative or abelian group, again we know that all the elements with respect to an operator should follow this expression, should follow this relation A star B is equal to B star A. Here this star is basically with respect to the multiplication operation. So, you take a field which is f with respect to your addition operation and the dot operator, and you take all the f star. How will you construct f star? Following this rule, f star will be constructed following this rule, and then with f star and f, if I see actually that with respect to multiplication operation the commutative rule follows, then we can say that yeah, this field can be also a ring. A field, it is also a set on which these two binary operators called this addition and multiplications are defined, and that contains two distinct element also which is actually 0 and 1. So, we came from the relation like this. So, we started with a set S. So, S with one operator either plus or dot, we turned to be a group. A group with its certain properties, I mean a set, a group, but definitely a special kind of the group which is said to be a abelian group if it is, and with the two operators we turned to be a ring. With ring, from ring we came to field now. So, if I see a field, field is also a ring. If a set and ring is also a group, definitely a field is a ring, field is also a group, and field is also a set. So, in the structure, algebraic structure of the field, if whatever the property a ring is satisfying, you will be able to see that all property of a group is satisfied in field, all the property of a ring is also satisfied in a field. In addition, the field with field needs to prove an commutative group with respect to its another set f star with the respective multiplication operation. So, that is another constraint to declare a ring to be a field. So, few more definitions, an understanding if the field with respect to your additive operator and a 0 identity element is an abelian group, and with respect to abelian group with respect to some addition and having 0 as the identity element there. If star with respect to my multiplicative operator and identity element 1, it is also an abelian group with respect to multiplication and having 1 as the identity element. Two operations like your which will linked by the distributive law, two operators, I mean this dot and this plus, they are linked, they can be linked with to prove the distributive law. The second distributive law, that b plus c into a is equal to b a plus c a, it follows automatically from the commutativity of the multiplication, and the elements, the 0 and 1, they are called the 0 element and multiplicative identity element, or simply the identity elements with respect to the operators. So, with this field, understanding of the field, the question comes, what is the definition of a finite field? So, we saw that a finite group will be constituting a finite number of the elements. In group also we saw there is a definition of finite group, infinite group, and hence the order of the finite group. There is no order in the infinite group definitely, but there is something called the order of the finite group. And similarly, in field also we will define the finite field. A field which contains all the finite number of elements will be called as a finite field. And the number of the elements, maximum number of the elements that you are constituting or you are seeing inside the finite field, which is called the order of the field. So, the maximum number of the elements that we see in a group, in a finite group, is the order of the group. We saw we write it like this. So, maximum number of the elements that we find inside the finite group is the order of the group, and the maximum number of the element that you see in a finite field is also the order of the field. It is the order of the field. So, this finite field was discovered by Galvez, and that is why the field is named after him and we call it Galois field. So, that is why the name is. So, basically they are the finite fields which we are talking about, and it goes after his inventor, name of his inventor Galois. This is a time to take some example. We will see that there are the well known sets which in form of with respect to other two operators can form the finite fields. Real numbers, okay, with the plus and minus operator, they are complex set of complex numbers with respect to the additive operator and multiplicative operator, a field. Q with respect to the positive operator as well as a multiplicative operator is also a finite field. We will take an example of the natural numbers of with modulo 2 operation on it with respect to your plus and dot operator to see actually that it is a finite field of order 2, and then let us see the elements of this field and how the table operation table on it will be generated. This is a very well known operation that we do in the first class of any digital communication circuit, and when we study all the gates in the digital communication and digital circuit also. So, the elements of this field Z2 are only 2 and they are 0 and 1. So, with respect to plus and with respect to dot operators, we will try to see how actually the operators are operating over the elements of this group, over elements of this field. So, this 0 and 0 with respect to the add operation, it will lead like this, and with respect to the dot operator, it will lead like this. So, 0 and 1 are basically the binary elements of this field. This very simplistic example we started with, and then let us see with higher number of the elements of a group and also of a field. Suppose we start with a Z5 plus dot. What is the meaning of it is this Z5. So, you take a set of the natural numbers and you each and every number you are dividing with the mod with 5, the n equal to 5 here, and whatever the remainder you are ending up with, you are then taking them in a typical set. If that is the situation, and then the elements of those fields are definitely you will be getting with 0 to 4, and the operation tables that we have shown here for both the operators are given by this. So, see, with respect to the 0, the first row of the addition we understand. Once actually the operation with 1 is coming up, now see beyond 3, when the addition is coming 5, which is not at all a number of this field, element of this field, and if we apply the modulo 5 operation for all this addition, definitely you will come down here as 0. So, the sum operation, after operation you are dividing it with the mod number, you are ending up. So, currently if I come here, so after this 4 plus 1 5, you are starting with the zeros, and hence actually these are all the remainders of the addition. After addition you are doing the mod operation, modulo operation, and you are ending up with those numbers. That is the way the whole operation table is written. I hope you have understood that the way the operator will operate is like this. Every element by element you do with respect to addition it is. So, you add their numbers and then divide it with the small n value with which actually it is constructed with. So, 0 plus 0 divided by 5 will lead you 0, no remainder remaining, and you are done here, the remainders are 0 only. Your remainders will be 1, 2, 3 and zeros only. But once you are up to 4 you are fine, but once actually you are doing with 1 you are trying to add all of them, because that is the way actually you have to perform the operation table. Once you are crossing the fiber number added number with equal to greater than equal to 5, then your number will keep on changing, your remainder values will keep on generating and you are filling it up with that. The same thing holds good for multiplication. Multiplication with zeros, in the first row will lead to you to 0, with 1 will lead you to up to 4, with 2 you are fine, but up to your 4, I mean 2 twos are, but in this portion you are not, because you have crossed the number 5. So, the remainder 1 will be 6 and you are ending up with the remainder will be 1 and you are ending up with that. So, 4 twos are 8 divided by 5 you will give you the remainder 3. So, you are ending up. So, that is the way the whole operation table is filled up. You can try at home with some higher one. Suppose if it is a natural number with the mod 7, modulo operation 7 with respect to plus and dot operator, try it out. To prepare this whole table, you can also try with some higher number which says Z11 with respect to plus and dot, and then you try to fill up all the tables. So, in general we will find that there are two following results are generating. Proposition number 2 is ZP with respect to dot and with respect to dot and with respect to plus, it is a field if and only if P is a prime. So, ZP anyway we have learned that if we write Z is a set of the natural numbers, and if I write it is P, that means it is a prime module after modulo P, if P is a prime number, and after the operation of the prime numbers on the number set, whatever the remainder is, I am taking them out, and with that only I have prepared the set. That set with respect to your addition and dot, it is a field if and only if the P is the prime number. So, we have to prove that number 1, that it is to come to be a field, we have to prove that they follow all the properties of the field definitely. So, from proposition 1 that we did earlier here, which we discussed in the last module also, I have not reproduced it here. We have also seen in the proposition 1 that ZP with respect to your additive operator and your identity element 0, and ZP star with respect to your multiplicative operator and your identity element 1, both are the abelian groups. If you remember that once we completed the description of a group, we prove this. We prove this, and we also prove in association with that, we also prove Zn dot 1. We also proved that Zp star dot 1 is a group. We proved that Zn with respect to 1 and 0 and Zp star with respect to dot and 1, they are the groups. And we also in this process it was easy, and we have also talked about that they are also the abelian groups. That means, all the elements of them, each of them which belongs to either Zp or Zn. If in case of my Zp star, if it belongs to Zp star, all that Zp or elements, they belong to this, they prove this typical relationship. So, they were the abelian groups. So, we proved that they are the groups, and we also this relation hold good. So, they were the abelian groups also. Extending the same logic, you can also show that the Zp with respect to your plus and 0 is also an abelian group. So, from the proposition we understand that both of them are the abelian groups, and because all the integers, any integer value, they satisfy the distributive law such that this will hold good. I mean, a into b plus c, if you do, you will be ending up with ab plus ac for any a, b, c which belong to the ZP. So, you can take an example also, and you can see that this distributive law holds good for this ZP. So, that their remainders are all equal. So, hence this ZP satisfies the distributive law. So, our first criteria to declare to be a field is that it should follow also the property of a ring, and in ring we saw that only the associative law was not sufficient. You should be allowed, it should be able to show that it follows the distributive law with respect to both the operators. See, with respect to both the operators here, I am seeing that actually the components of this ZP, set ZP, they satisfies the distributive law. And according to the definition of the fields, this is also a field that we did earlier. The definition of a field says that you have to have another set prepared from this field, from the ring, if it is a ring already. So, ZP star, where all the elements will be part of that ring, earlier ring ZP, given that A is not equal to 0, and the element by element wise it will form a commutative law. So, the commutative law for the prime numbers is already proven, and hence we can declare that ZP with respect to your plus and dot, it is definitely a field. Note here that one part is left. The converse of this proposition is also true, that if a set of the natural numbers, it should be written like this. If the set of the natural numbers with respect to the plus operator and dot operator is a field where your n is greater than 1, and n is a positive integer, then n must be prime. I mean, for if p is a prime number, then this is a field. This is a forward proof. And if this is a field, if given this is a field and n is a greater than 1 number, then to prove that it will be a field, definitely to prove that this should be a field, n should be a prime number. So, it is vice versa, and we understand that this ZP plus and dot is simply denoted by ZP for the for either will be denoted simply by the ZP, or we will write it as a Galois field P. So, remember that which is called the residue class field of modulo P, whatever you say, because this is the modulo P operation on your natural numbers. So, when we write that the Galois field 2, so it means that it contains the only two binary numbers, only two numbers, zeros and ones, and those numbers are the prime numbers, and we can actually construct all the typical sets and all the typical working tables for them with respect to both the operators. So, from now onwards, so when we will talk about the fields, so if they are the finite fields and they are of what is the modulo operation going on that field, we will either write in this form and preferably by the GFP, stating that these are the finite Galois fields with respect to their prime number